Hi guys, and welcome to this lecture. This is basically the introduction to color processing. Okay, so basically, although color sounds like a relatively straightforward concept, different representations of color are useful in different contexts. Okay, so in the LabVIEW vision framework, the colors of an individual pixel are processed with color using the color library in the LabVIEW Vision Assistant. Let's just take a look at what we're going to be dealing with. Okay, so we all know what RGB is. For those who don't, it is red, green, and blue. This is our full image. This is what our image composes of, but it can be divided into three components, which are the red component, green component, and the blue component. If you combine these three components, we'll get this full image. For those who know that your TV, it comprises of red, green, and blue pixels. For the new TVs, they come with a luminance pixel or a white pixel. Here's another example of RGB. So we have the original image and can be separated into the R, G, and B component. Okay, so let's look at another way to represent color, which is called the HSV. So one criticism of RGB is that it does not specifically model luminance. Yet the luminance or brightness is one of the most common properties to manipulate. In theory, the luminance is the relationship of the R, G, and B values. In practice, however, it is sometimes more convenient to separate the color values from the luminance values. The solution is the HSV, which stands for hue, saturation, and value. The color is defined according to the hue saturation, while the value is the measure of luminance or brightness. And the HSV color space is essentially just a transformation of the RGB color space, because all colors in the RGB color space have a corresponding unique color in the HSV space, and vice versa. Let's take a look at an HSV example. So we got our full image, and then it's separated into hue, which is the different colors, and that also comprises of the saturation, which is the colorfulness, as well as the value, which is the brightness or intensity. Here's another example. We got the hue with the different colors. We got the saturation, how saturated it is, and the value, which is the intensity. Okay, let's look at the RGB relation to HSV. So the HSV color space is often used by people because it corresponds better to how people experience color rather than RGB color space does. So here is a representation of how it looks. So you got your hue, you got your saturation, how saturated it is, and then the value, how dark or light it is. In LabVIEW, we use the color space or color plane extraction, which is used to extract either the RGB or HSV information from an image that we can access using the color palette over here. And from here, we use color plane extraction, and we can either choose the RGB, red, green, blue plane, or the hue, saturation, and luminance plane. Okay, so the HSV color space is particularly useful when dealing with an object that has a lot of specular highlights or reflections. In the HSV color space, specular reflections will have a high luminance value, V, or a lower saturation component. The hue, H component, may get noisy depending on how bright the reflection is, but an object of solid color will have largely the same hue, even under variable lighting. Let's take a look at color and segmentation. Segmentation is the process of dividing an image into areas of related content. Color segmentation is based on subtracting away the pixels that are far away from the target color, while preserving the pixels that are of similar color. The image class has the function that computes the distance between every pixel in an image and given color. This function takes an argument, the RGB value of the target color, and returns another image representing the distance from the specified color. Okay, looking at a segmentation example. If we take our input image, which is this glue gun, we segment only the yellow part of it. So we segment that, we binarize it, so you get either a 1 or 0. So this black being 1, white being 0. And then we create a mask from this, and we overlay the yellow over that. And then we get only the segmented image. This is particularly useful in object tracking or color tracking, or you can use it for doing measurements, such as what is the length from this edge to this edge. To do that on here, it is possible, but it is easy to do it with a binary image. Okay, so in the next few lectures, we're going to be building some vision apps. So the vision app number 1 is to count M&Ms. So it's basically a simple app, but we'll be able to count how many green M&Ms there are, how many blue M&Ms there are. Red is a bit tricky because orange may look similar to red in some cases. But you should remember that in image processing, you may not get 100% detection rate. So that's why computer vision is an ongoing study and field. Okay, take a look at Vision app number 2. We're going to be doing color tracking app. So this will take, say if you have an orange ball or blue ball or any color ball, and that ball is different from your background, you will be able to track that ball through your space as you move it in and out of the camera. Okay, so I hope you're looking forward to doing that, your first vision-based apps. And this is your first step into image processing and to creating cool apps that you can use for future applications. Okay, see you in the next lecture.